is less or equal to B if and only if the product AB is equal to A. And this relation makes E lower semilattice. Is a partial order. This relation is a partial order. Is a partial order on E, and not only partial order, it's also a lower semilattice. And this set E together with this relation partial order is a lower semilattice. Is a lower semilattice. Okay. So it's actually if and only given a commutative semigroup with each of its elements is idempotent, then one can define a relation on E such that that relation makes E a lower semilattice. And conversely, given a lower semilattice, we can define a binary operation on E such that that binary operation on E makes it a commutative semigroup with each element of E is idempotent. Okay. So let's prove this. So clearly, it's a semigroup. It's already proved. This one, it's a semigroup. This is already proved. It's a semigroup. Okay. So suppose A with this relation is a lower semilattice. Is a lower semilattice. So then meet exists for any two elements, and that meet operation makes E a commutative semigroup. Then this E with meet operation, because it exists for any two elements, is a semigroup. It's a semigroup. That's simple. That's not too difficult. It's a semigroup. And it's a semigroup. Also this A meet B is equal to B meet A for all AB belongs to E, and A meet A is equal to A because but A meet A can be written as A square because this is the operation between the two elements A and A. So A meet A means A square. So A square means A meet A. Meet is the binary operation, and this A meet A, it's the greatest lower bound of A and A, that's equal to A. So therefore, this semigroup, it's a commutative semigroup because this one it's the greatest lower bound of A and B, and this one it's the greatest lower bound of B and A. So both are same. So that means it's a commutative semigroup, and this one A square, it's equal to A meet A, which is equal to A. So that means A square is equal to A for all A in E. So therefore, E is a commutative semigroup with each element of E is an idempotent. Therefore, A with this binary operation is a commutative semigroup. Commutative semigroup is a commutative semigroup with each element of E is idempotent. Is it idempotent? With each element of E is an idempotent. Is an idempotent. Is an idempotent. So that proves this part. So this then is a commutative semigroup with each element of A is idempotent. And one more thing, we have to prove that this, if A is less or equal to B, we need to show that A meet B is equal to A. Now next we show that A is less or equal to B if and only if meet of A and B is equal to A. So assume that assume that A less or equal to B. Okay, since A is also less or equal to A because it's a reflex relation, so that means A is lower bound of A and B. So therefore A is lower bound of this set AB. But we need to show that it's the greatest lower bound. So for this we take any lower bound of A and B and we will show that this A is greater or equal to that lower bound. So let's take any lower bound. Let C be any. Let C be any. Let C be any lower bound of A and B. Then C is less or equal to A and C is less or equal to B. So this means this C is less or equal to A. So that means A is the lower bound of A and B and A is greater or equal to every lower bound of A and B. So which means that A is the greatest lower bound of A and B. So A is equal to A meet B. A is equal to A meet B. And now we assume that suppose this A meet B is equal to A, we need to show that A is less or equal to B. So conversely assume A meet B is equal to A. So that means A is greatest lower bound of AB. So which means A is less or equal to A as well as A is less or equal to B. So we need this A is less or equal to B. So whenever A meet B is equal to A, then A is less or equal to B, and whenever A is less or equal to B, then meet of A and B is equal to A. So this proves one way. Now we assume that this we have a commutative semigroup. We need to show that commutative semigroup with each element of E is idempotent generates the partially ordered relation on E, such that that relation makes E lower simulates, makes E lower simulates. So now we prove its converse part. So what's the converse part? So that's for the direct part. Suppose it's a lower simulates, then it's a commutative semigroup with each element of E is idempotent and it also satisfies this property. And the converse part is this. Suppose this is a commutative semigroup with each element of E is idempotent. We need to show that there is a relation which is defined by this. That one. So we show that this relation is partially ordered on E, and with respect to this relation, it's a lower simulates. Okay. So conversely assume that E with the operation dot is a commutative semigroup with each element of E is an idempotent. Now we define a relation. Define the relation on E by define this relation on E by A less or equal to B if and only if A meet B is if and only if the product, sorry, we don't have meet here, A dot B is equal to A. A dot B is equal to A. So we show that this relation is partially ordered on E. So first property, we have A dot A which is equal to A square, that's equal to A. So that means A dot A is equal to A. Whenever A dot B is equal to A, then this A is less or equal to B. So this is true for all A belongs to E, because every element of E is an idempotent, that means A square is equal to A. So but this one, it gives A is less or equal to A for all A belongs to E. So that proves the first property, it's reflexive. Now second property, this one is the reflexive property. Second is antisymmetry. and be symmetrical. So suppose A is less or equal to B and B is less or equal to A. We need to show that A is equal to B. But whenever A is less or equal to B, it means that A into B is equal to A. So A into B is equal to A. And whenever B is less or equal to A, it means that B into A is equal to B into A is equal to B. So this means B into A is equal to B. But since our semigroup is commutative, that means A dot B is same as B dot A. So which means that A is equal to B. This means that A is equal to B because A dot B is same as B dot A. So therefore relation is anti-symmetric. So next we show that it's also transitive. It's also transitive. So for this we choose any three elements A, B, C in E such that A less or equal to B, A less or equal to B and B less or equal to C. We need to show that A is less or equal to C. But this one A less or equal to B, it means that A dot P is equal to A and this one B dot C is equal to B. So we need to find AC. We need to show that AC is equal to A. So that will give A is less or equal to C. So for this we calculate AC. What's AC? A into C. Okay. A into C. A is same as AB. It's equal to AB. A same as AB is equal to A dot B dot C. Now apply the associative property. It's A dot B dot C. What's B dot C? B dot C is B. It's A dot B. Then A dot B is A. So that means A dot C is equal to A, which gives A is less or equal to C. So therefore A together with this relation less or equal to is a partially ordered set. Is a partially ordered set. So next we need to show that it's actually a lower semillatice. It's lower semillatice. It's lower semillatice. That's here lower semillatice. So this one, this is a commutative semigroup with each element of E is idempotent. This relation is a partially ordered set. Is a partially ordered on E that we have proved. So now we show that this is lower semillatice. This is lower semillatice. This is lower semillatice. Okay. So for the lower semillatice, we need to show that for any two elements A and B of E, their greatest lower bound exists. So let A comma B belongs to E. A comma B belongs to E. A comma B belongs to E. So A comma B belongs to E. So we show that A into B is actually it's the meet, and A into B it is in E because E is a semigroup with multiplicative operation. So if we will prove that A dot B is equal to the greatest lower bound of A and B, then we are done. So that means the greatest lower bound of any two elements exists in that case. So we have first we show that A dot B is lower bound of A as well as B. So for this we calculate this A into AB, it's equal to A square B, that's equal to AB. That's equal to AB. So which means that this means that AB is equal to, using the commutative property, AB is equal to AB into A. So this is the element. AB is equal to AB into A. So what's the relation? What's the definition of relation here? what's the definition of the relation here? A is less or equal to B if and only if their product is A. Their product is the first element, and here the product of AB and A is the first element AB. So which means that AB is less or equal to A, because their product AB into A is equal to AB. So whenever this AB is equal to A, that means A is less or equal to B. That's the definition of relation. A less or equal to B means A dot B is equal to A, or A dot B is equal to A means A is less or equal to B. So the product of A and B is equal to A, it means that A is less or equal to A. So here product of AB and A is AB, so that means product of AB and A is AB, so it means that AB is less or equal to A. So next we see that AB is also less or equal to B. AB is less or equal to B. For this we find the product of AB with B. AB into B, that's equal to A times B square, but B is idempotent, it's AB. So product of AB into B is equal to AB, so which implies that AB is less or equal to B also. So therefore A into B is actually lower bound of AB. It's lower bound of AB. But we need to show that it's the greatest lower bound. So for this we choose any lower bound of AB. Let C be any lower bound. Let C be any lower bound of AB. Let us choose any lower bound C of AB. Any lower bound C of AB. So then since C is the lower bound, it means that C is less or equal to A and C is less or equal to B. C less or equal to A means C dot A is equal to A dot B is equal to A. Okay, C dot A is equal to C and C dot B is equal to C. Then we show that this C is less or equal to AB. That means AB is the greater or equal to every lower bound. So we will show that C dot AB. We show that C is less or equal to AB. Actually, for this we need to show that C dot AB is equal to C, and that's equal to C dot A by associative property. What C dot A? It's equal to C. C dot A is equal to C dot B, and C dot B is equal to C. So that means C is less or equal to AB. So we have shown that AB is the lower bound of A and B, and for any lower bound C of AB, C is less or equal to AB. So which means that A dot B is the greatest lower bound, is the greatest lower bound of AB. That is this A dot B is equal to A join B. So hence, and it belongs to E. So hence E with the relation less or equal to is a lower semillatice. And we have a similar result for upper semillatice. So in the case of upper semillatice, we finally get A dot B is equal to A join B in that case. So by lower semillatice, so therefore whenever we have a lower semillatice, we can always treat it as a commutative semigroup with each element of each of its element is an idempotent. So that's the definition of lower semillatice.